Hi, and welcome to CIS 113, and we are going to basically be covering the uh, book that talks about logic. And let me show you the cover. So it's starting out with Programming, Logic, and Design by Tony Gaddis. With this section, we're going to cover Chapter 1. So Chapter 1 is going to talk about hardware and how basically computers look at data and how they interact with data and all the different things and pieces and parts that make up a program and how a program interacts with the computer. Okay, so I don't want to spend a whole lot of time on some of these things because you can read these for yourself. So I will cover a lot of these at a high level. So again, we do have a computer. The main piece of a computer is this thing called a CPU, or central processing unit. Think of it as the brains of the computer. We also have this main memory, also known as RAM, random access memory. And it basically, what I want you to think of RAM is think of RAM as a dry erase board that the CPU uses to basically work out different calculations. So, how we get data into this main memory that the central processing unit will use is we will use hard drives, thumb drives, all kinds of different input devices that will allow us to get data in that way. As they show here, they've got webcams and joysticks and scanners and keyboards and mice. Those are all input devices that get input into that main memory that the CPU uses with their little dry erase board to kind of work things out. And then they will send that out to either a monitor or a printer or speakers or some type of output device. Could be a robotic arm, could be some type of piece of another computer equipment that basically does some type of a different learning thing. So how does this all work together? Well, they kind of show you some of the different things here. But so here's what a RAM looks like. It's made up of silicon chips that go anywhere from a couple gigabytes to 1632, 48 gigabytes. Secondary storage devices, we're talking about hard drives, we're talking about CD-ROMs, we're talking about thumb drives, all that type of thing as well. So how we can kind of have storage outside of the computer itself. You probably know about how bits work. We have a byte, which is made up of 8 bits, and a bit is either a 1 or a 0. And the way they illustrate here, it's a switch. It's either on or it's off. So if a bit is on, then it's a 1, and we combine those 8 bits together, which basically becomes a byte. So here is the number 77 stored as a byte. So the first one's a 0, 1, 0, 0, 1, 1, 0, 1. The letter A is 0, 1, 0, 0, 0, 0, 0, 1. Okay. So how we basically look at this. So when we start on the right hand side of the byte and looking at the bits, we see that this first bit is 2 to the 0 power, which is basically 2. I'm sorry. Which is 1. I'm sorry. So it's a 1. Right. 2 to the 1 power is a 2. 2 to the 2 power is a 4. 2 to the 3 power is 2 times 2 times is 8. 2 to the 4th power is 30. Oh, here they are down here. So anyways, so here's how this works. If I look at this bit, now what I want you to think about is a language called hexadecimal. And or not a language, but a numbering system called hexadecimal. It's a 16-base numbering system. We're used to a 10-base numbering system, 0 through 9. If we had a 16-digit numbering system, we would have 0 through 9, then A, B, C, D, F, then 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 1A, 1B, 1C, 1D, 1F, 20. Okay, that's a 16-bit or hexadecimal numbering system. So what we can do with this is we can actually get all of the numbers we want between 0 and 256 through these bytes. So for example, I have, so if this is the byte, I would look at this one, I would take, that's a 1, that's a 4, 1 plus 4 is a 5, that's an 8, 1 plus 5 is 13, I would add 32, which is 42, 45, and then I would add 128, and again, so anyways, I'd add those numbers up, and then that would get me a number between 0 and 255. In this case, it's 157, and again, that's kind of looking at our switch here, on, off, on, off. So we add those numbers together, we get 157, and now I can actually look that particular item up and basically get the hexadecimal representation of that number in some type of a table. Back in my day when I first started programming, we had this, what we call the IBM yellow card, and we'd actually look up that yellow card. I still have one, and I could look up that hexadecimal or the numeric, the 0 through 254, this 255, so 0 to 254, and that would basically give us a number, a letter, lowercase number, whatever the case may be. So again, pictures are stored as bits and bytes. That's really all they are. All data is stored as bits and bytes. So that's the whole point they wanted to get across in that little section, is think of every piece of data, whether it's an audio, whether it's MP3, whether it is I don't know, some type of, file of any kind of data is basically a bunch of zeros and ones. That's really all that it is. And they combine those together, the bytes, and then the bytes get basically combined together into kilobytes and megabytes and gigabytes and terabytes and petabytes, and it basically goes on from there. So this little item right here is trying to show how we get data off of our hard drive. It gets loaded into our memory, and then the CPU works directly out of the main memory to basically work on data, whether it's a program, whether it's a file that it's read, whatever the case may be. That's how it's utilized. So it's loaded in the memory. Now the one thing you should note, and I think they'll go into this a little bit later on, is the operating system is also running in a section of the main memory. There's a little bit of the main memory is kind of put aside for the operating system so that we can kind of run. So when a CPU executes instruction in a program, it is engaged in a process known as fetch, decode, execute cycle. The cycle consists of 3 steps, which is repeated for each instruction in the program. So fetch, a program in a long sequence of machine language instructions. So it basically gets the actual code. The first step of the cycle is to fetch or read the next instruction from memory into the CPU. So as this program is running linearly, it's hard for me to say, it basically will grab the next line of code, put it in memory, and then the decode, a machine language instruction, is a binary number that represents a command that tells the CPU to perform an operation. So that machine language, now only the CPU understands machine language. We as human beings cannot read machine language, and we'll kind of get that a little bit later on. It reads that machine language, and then it executes that particular line of code. So it fetches, decodes it, and then basically executes. Now decoding may be a compile statement. It may be we have our particular line of code. It's English-like for Java, whether it's C#, C++, whatever the language is. It's English-like that we understand as humans, but then it's converted into or decoded into machine language and then basically executed. So it talks about from machine language to assembly language, so computers can execute programs that are written in machine language. As previously mentioned, a program has thousands or even millions of binary instructions. And writing such a program could be very tedious and time-consuming. Although a computer CPU understands machine language, it's impractical for people to write programs in machine language. We just can't do it as humans. For this reason, assembly language was created in the early days of computing. So assembler is a language that was written where you had to lay out every single step of the program. Today I can just say loop and it will loop. With assembler, I would have to actually step through that loop and all of the different executions within that loop in order for it to execute. So assembly language is more machine-like than it is code-like. And so it took a lot less to basically convert assembler into machine language, and thus, again, assembler is more a machine language-like as opposed to what we call high-level languages today. So here are COBOL, Pascal, C, C++, C#, Java, JavaScript, Python, Ruby, Visual Basic. This is just a small portion of a very, very large group of high-level languages. This class is going to basically lead us into the next class, which is going to get us into Java coding. If you get into other languages, you'll see a lot of similarities between C# and Java, a little bit of JavaScript. Python is a lot like Java. Visual Basic is, the structure is the same, but the language is a little different. So a lot of differences between the languages, a lot of different powerful things each language can do. So what we need to do is, for example, here is display hello earthling. Okay, that's a line of code in some language. The compiler then converts that into machine language, which is a bunch of ones and zeros that the CPU can understand. Okay, and then the CPU again does the fetch, decode, and execute steps, a cycle, through each one of these different lines of code, machine language code. So we have this thing called IDE, or what is called Integrated Development Environments. It says, although you can use a simple text editor such as Notepad to write a program, most programs use this thing called an IDE. For example, in Java we use an IDE called Eclipse, and it's a nice free download and allows us to write our code and actually execute it, and it basically is structured in Java, so it gives us all the structure that we need for Java. So it shows reserved words a certain color and basically indents properly and all the things needed for Java. Here they are using Microsoft Visual Studio, so this is probably this is a Visual Basic program, and this is what VB looks like. Yeah. So we write this, we compile it into machine language, and then it can be executed. So different types of software that are out there. We have operating system, which is probably the one we all use, whether we use a Mac, whether we use Linux, whether we use Windows. We have an operating system, which is software running in the background, allows us to interact with the actual CPU through our operating system. We have utility programs, which basically kind of keep, they're like the toolbox that we use to get certain things done. And then we have software development tools like Eclipse, and some of these other tools allow us to write programs, Visual Studio, to basically get these programs written that we can then utilize. Windows, iOS, Mac OS, and Linux. A lot of the different languages or operating systems that are out there. Application software. This is software like Microsoft Word, Microsoft Excel, that have a specific purpose. Word allows us to create Word or textual documents that are formatted. Spreadsheets allow us to do these cell processing, have different formulas and things that we can do to crunch numbers. PowerPoint is a way for us to display a presentation graphically up on a screen. So, okay, so that's pretty much it for chapter 1. I'm going to go ahead and just jump over into chapter 2, and we're going to get directly into that because we're going to cover chapter 1 and 2 the first week. So we talk about input, processing, and output. So we kind of see what that is with the CPU. CPU takes things in, it processes it, and then it basically spits it out. So we're going to get more depth into that. So the very first thing it talks about is this thing called the program development life cycle, and what that means is once you write code and now it's out there being used, at some point we're going to have some type of maintenance on that code. For example, I work for an insurance company. Some of the programs I've written in the past, we were basically regulated by the government to produce these certain reports. Well, as those reports change, we get upgrades or updates from the government saying we need this particular program to now look like this, or this report to look like that. So we'd have to go into our programs and basically make an update. So if we're creating from scratch or whether we're making an update, we have to design the program. Okay? And that's kind of what this class is all about, designing the program, getting the logic worked out. Then we write the code, we correct any syntax errors, we then test the code, we debug the code, and there should be one more step here that says we actually put the code into production. Okay. Then as we get maintenance, we pull it back out of production, we design the program or design the changes and updates, write the code for that particular update, correct it, test, debug, go from there. So this class again is about logic. How do we design a program? We want to work on the logic of this program. So first thing we need to do is understand the task. What is it that somebody basically needs completed here? Okay, so we have to determine what steps need to take place in order for this particular thing or process or steps need to basically be done in order for this task to be completed. So for example, suppose your little sister asks you how to boil water. Assuming she's old enough to be trusted around the stove, you might break down the task into a series of steps. First thing you do is pour the desired amount of water into a pot. We put the pot on the stove. We turn on the burner. We watch the water until we see large bubbles rapidly rising. When this happens, the water is boiling. Okay, so we broke it down into steps. This example is what's called an algorithm, a series of steps. You can't do step 2 until you do step 1. You can't do step 3 until you've done step 2, and so on and so forth. So this is well-defined logical steps that must be taken to perform a task. Notice the steps in this algorithm are sequentially ordered. Step 1 should be performed, step 2, so on and so forth. Programmer breaks down the tasks that a program must perform in a similar way. An algorithm is created, which is a list of logical steps. For example, suppose you have been asked to write a program to calculate and display the gross pay for an hourly paid employee. Here are the steps. We get the number of hours worked. We get the hourly pay rate. We multiply the number of hours worked by the hourly pay rate. We display the result in the calculation that was performed in step 3. Okay, it's as simple as that. So what we're going to use primarily in this class is this thing called pseudocode. And I want you to think of pseudocode as just English. That's all it is. It's just English. So here's an example of how we might write pseudocode for calculating that process we did just a second ago. Display, enter the number of hours the employee worked. Input hours. Display, enter the employee's hourly pay rate. Input pay rate. Set gross pay equal hours times pay rate. Display the employee's gross pay is $ gross pay. So it looks kind of weird, but what's nice about these steps is we can easily convert them into any language we're going to use. I can take the pseudocode and put it and give it to a VB programmer, and they can write code from it. We can give it to a Java program. They can write code from it. We can give it to a Python, COBOL, Pascal, whatever the case may be. We can give this pseudocode. So this pseudocode is universal. We can give it to any programmer in their specific language, and they can write code in that language to execute the task that needs to be displayed. In this case, gross pay. Okay. So another thing we can use is this thing called flow charting. Now, when I first got into programming, we had to use flow charting to design our logic. We had to use stencils, pencils, and erasers to draw these symbols. Well, we have software that will do that for us today. So we always have a start, we always have an end. When we have these parallelograms, these are instructions for someone, okay? Or it's a way to get input. So these parallelograms is basically an instruction for someone to basically get, whether it's input, whether it's output, but we're actually getting some type of instruction from something. So display the in and hours worked, input hours, display the employee's hourly pay rate, and then input the pay rate. Now we have a rectangle. This is actually a calculation. This is going to do some type of computer calculation or some type of executing of code. And then we display whatever was basically calculated right here, and then the program ends. So we always have to have a beginning, we have to have an end. Okay. Now, if I needed to split this off, for example, I wanted to put this in two different columns, I put a circle with an A, and then the A says I continue over here. That's as simple as that. Or we can use what I call the home plate symbol. We can use that as well. And we would use that more if we're going from one page to another. So here's page 1, here's page 2. This says, hey, go to this goes to page 2, and this is continued from page 1. So, input, output, and variables. So we have these things that are called variables. Variables hold data. Okay, and think of a variable as a temporary place to store data. So, for example, computer programs typically perform the following three-step process. Input is received, some process is performed on the input, and then the output is produced. Okay, so here I've got hours worked, I've got hourly pay rate. They're brought in, here's the process. We multiply the hourly pay rate times the hours worked, and the output is gross pay. So here I see three variables. Hours worked is a variable, hourly pay rate is a variable, and gross pay is a variable. So I basically have hours worked is going to hold a numeric number of the hours worked by that employee. The hourly pay rate is the pay rate that that employee basically gets paid per hour. The gross pay is going to hold the calculation of those two numbers multiplied together. So there's three variables. So we have these things called IPO charts, which is input, processing, and output charts. This is another way we can kind of document our code and our process. So in this case, I've got, we like to have a three-column table to do this. I have input, I have processing, I have output. So in this case, my input is number of hours worked and hourly pay rate. The processing is to multiply those two together, and result is to create the gross pay, and the output then is the gross pay. There's our IPO chart. It's as simple as that. Okay. A way to display screen output in this book, we are going to use the display to write our pseudocode. So if I need to display or show something on a screen, I can just say display gross pay. Now, whatever language we're going to use, then you'll need to know how to display that on the screen with that particular language. Okay? So yeah, here I have start, display display this address, display the city, state, and zip, and then end. And that would basically how it would look on a command line. So sequence structures, as mentioned earlier, the statements in 2.1, these three display statements, execute in the order they appear, from the top to the bottom. A set of statements that executes in the order as they appeared is called a sequence structure. That means this is going to execute before this one, this is going to execute before that one, and then it's going to basically be done. So it will display it just like in this screen right here. So when we write our code, that's exactly how it's going to execute, in a sequence structure. Then we have what are called strings and string literals. I want you to think of data types now. We need to think of data types. So we have numerics, we have true false, we have this other thing called string. Now string is just text. You cannot do any calculation on a string because it's textual. Can strings contain numbers? Yes. We would always make a zip code a string data type. We would never make it numeric. And the reason we would never make it numeric is if you have a zip code on the East Coast that starts with 0, you're only going to get four numbers back. That first number will not contain anything. If we made it a string or textual, we would see that we would have 4 digits as opposed to 5 digits. Okay? So a nice way to get our data. Now string literal is just that. If I put some text with double quotes around it and say display that, that is called a string literal. That's not a variable. Okay? If I say display gross pay is a variable. It contains numeric data. We're going to display the numeric data. If I say display Mark Webb with double quotes on it, it's going to display Mark Webb. There's no variable holding that data. So that's called a string literal. So variables and input. So the word input is an instruction to read a piece of data from the keyboard. The word hours is a name, the variable in which the data will be stored. So I say input hours. That means I'm getting data from somewhere. Could be the keyboard, could be the hard drive, could be a file that I'm reading, whatever the case may be, I'm getting that input. Again, it's up to the programmer, it's up to whoever to basically decide where that input's coming from. But in my pseudocode, I'm just going to say input hours. I'm getting the hours from somewhere. Hours is my variable. It's holding the numeric data that I'm getting from somewhere. It's going to be holding the hours that particular employee worked. Okay. So display what is your age? Input age. So on the screen it's going to say what is your age, and then I say input age. So in this case we're having the user type in their age, and then we capture that numeric data and put it in that variable called age. Then I say display, here's the values you entered, display age. Now I display, here's the values you entered, and then I display age. So whatever data is inside of age, that will be displayed on the screen. What is your age? 24. Enter. Here is a value entered, 24. So basically this is what it would look like on the screen. Okay. The word enter would not show up. What they're saying is they typed in the number 24 and hit the enter key, and then here's a value entered, 24. Now if you notice, I've got display age and I've got display double quote age. Now, how are those different? Well, age right here is a variable. It can contain data. If it has the number 24 in there, it's going to display the number 24 on the screen. This one is a string literal. It will actually display the word age on the screen. So that is a string literal, that is a variable. So if you see double quotes around something, that is a string literal. Now I can make a variable equal to a string literal. Okay, we'll see that later on. So here's the flow chart of that last program that we basically did. Start, display what is your age, as that's displayed on the screen, input age, so we get whatever they typed. We display here's the value you entered, that's displayed on the screen, and then we say display age, and we display whatever data they typed in got put into that variable. And then we basically end the program. Variable names. At high-level programming languages allow you to make up your own names. Okay, so we can make up any name we want. I highly suggest that we use what I call good variable names. I heard of a story of a programmer who wrote everything in a Alice in Wonderland motif, meaning all the variables were Alice in Wonderland characters. Tweedledee, Tweedledum, Jabberwocky, basically any type of Alice in Wonderland character. Well, what makes that bad is when I say add Tweedledee and Jabberwocky to get the Red Queen. What does that mean? That means absolutely nothing to the programmer. But well, let's say I had a variable name called tax rate, and I had another one called total sales, and I had another one called grand total. If I said grand total equals total sales times tax rate, I would basically then have, I would know what those variables mean. So using good variable names is very, very important, because the one thing we always have to think about when we write programs is we are not going to be the ones that maintain those programs, meaning you're going to write it and somebody else is going to maintain it. So we always want to make sure that we use good names and basically good logic, good sequence, structured sequence, and then that program will be easy to read, maintain, and basically take over. So gross pay, pay rate, hot dogs sold today, those are good. And to make it easier to read, we might say gross underscore pay. We would never use a dash. The reason we don't use dash is that's a minus sign. So if I had gross minus or gross dash pay, it thinks it wants me to take gross and subtract pay from it. It thinks of those two separate variables. So we always use underscores. Pay underscore rate, hot underscore dogs underscore sold underscore today. Again, hot dogs sold today. Wow, can that be anything else? No, we know exactly what that variable means. So good variable names. We can also use a thing called camel case. I can say gross pay, the P in pay is uppercase. Pay rate, the uppercase and R is uppercase. So it separates the words as well. So if you don't want to use underscores, you can use camel casting. Display multiple items with one display statement. I can say display here is the value you entered and display age. Or I can say display here's the value you entered, comma, age. So it's a nice way to put it on one line, so we're able to do that because other languages can do that as well. So we could do that within our pseudocode. And we do that now. Make sure when I type in here is the value entered colon, make sure you put a space there, because this is a string literal. That's going to actually display on the screen. And if you have age, if you did not leave that space there, whatever number you typed in is going to be up against that colon. So you have to think about that as well, because this is what it's going to look like when it's done. Here's the value entered colon space 24. Other word 24. Now is that bad? It might not be bad, but we have to make sure that we always have our stuff formatted properly as well. So string input. So I want to get string input. That's text input. Display enter your name, input name. Display enter your age, input age. Display hello, name. Display you are blank years old. Okay, so it'd be enter your name, Andrea, enter your age, 24. Hello, Andrea, you are 24 years old. Okay, So prompting the user, we need to prompt the user to get data from the user. So we can display a prompt on the screen, we can read a value from the keyboard. So we can say input, what is your age? Input age. So the prompt is the message, which is what is your age? That's the prompt. We're prompting the user, hey, I want data from you. This is the data I want. I want your age. Okay. In most programming languages, the statement that reads the keyboard input does not display instructions on the screen. It simply causes the program to pause and wait for the user to type something. So we have to type in that display message first. Then the input statement gets whatever they type in. So it's very important that we understand that. I just can't say input age, because the input statement does just that. It just gets whatever they type on the keyboard. They're not going to know. Okay? We have to let the user know what they need to type in. So variable assignment and calculations. So we create variables. We can assign data to each of those variables. So I can say set price equals 20. So that's a nice way to say, hey, I've got this variable called price. I don't want to make it equal to 20. So I say set price equal 20. This is called assignment statement. The assignment statement sets a variable to a specific value. The variable price is set to 20. When we write an assignment statement in pseudocode, we write the word set, followed by the name of the variable, followed by the equal sign. Okay. The pseudocode shows another example. One, set $. Okay. Display I have dollars in my account. So here I've got two string literals on either side of a variable separated by commas. A comma is a way we separate, because think of those as three separate statements. And so as I have as a string literal, so it actually prints a string literal of I have. Notice I've got a space, because if I didn't, 2.75 would be butted up against the E and have. And then I say in my account. Notice there's a space in front of the word in, again, so that we have a space between 275 and the word in. Set $. Equals that. Display I have blank dot. Set dollars to 99.95. Display, but now I have, and so it's going to display I have 2.75 in my account, but now I have 99.95 in my account. So again, since this is sequential, it's going to do that one first, then that one, then that one, then that one. So set statements are rectangles, because it's actual code that we basically will write. Displays are basically a way to display or do some type of a command that the user, in this case, will see the word I have dollars in my pocket. And I set the dollars to something else, and then, but now I have this. So again, they're command things that we're displaying on the screen. That's when we use a parallelogram. So calculations, we have addition, subtraction, multiplication. We use asterisks. We don't use an X, because an X can be a variable or a letter. So we don't use an X. We use an asterisk to do multiplication. We use a / to do division. We do use mod to do what's called modulus. What modulus does is when we divide one number from another, a modulus will return to us the remainder. Okay. We use modulus to find out if a number's even or not. If I take this number divided by that number by 2, if I get back 0 modulus, I know it's an even number. And then I have the caret symbol, which is an exponent. So if I say 2 caret symbol 3, that's 2 to the 3rd power. So 12 plus 2, hours times pay rate, set price equals 100, set discount equals 20, set sale equal price minus discount. So now I take 100, I subtract 20, then I say display, the total cost is $ sale, and it will display the total cost is $80. Now in this case here, I did not put a space after the $, because I do want the number butted up against that $. Okay, so this is something you probably want to do maybe on your own. They kind of give you the answer down here, but again, Manual algorithm, use pencil and paper or calculator. When you get the number of excess minutes you have used, multiply the number times 0.35. The result of the calculation is your current overage fee. So here's what we need. Suppose your cell phone calling plan allows you to use 700 minutes per month. If you use more than this limit, you are charged an overage of 35 cents. Your phone shows the number of excess minutes that you have in the current month, but it does not show how much your overage fee currently is. Until now, you've been doing the math the old-fashioned way with pencil and paper, but now you'd like to design a program that will simplify the task. You should be able to write and enter the number of excess minutes and have a program perform the calculation for you. First, you want to make sure that you understand the steps of the program. So the manual algorithm is what I just talked about. You get the number of excess minutes that you have used. You multiply that by 0.35, and the result is your current overage fee. Okay, so they say you should ask yourself these questions. What input do I need to perform this algorithm? Do I need the number of excess minutes? That's the answer. What must I do with the input? I must take and multiply that overage minutes times 0.35. How is the output produced, or what output is produced? The overage fee is basically displayed on the screen. So, computer algorithm, get the number of excess minutes as inputted. I'll calculate the overage fee by minutes, the number excess by 0.35. Again, take the overage minutes times 0.35, and then we display that on the screen. Okay, so we'd say display, enter the number of excess minutes, input the excess minutes. Set the overage fee equals excess minutes times 0.35. Display your current overage fee is $, comma, overage fee. Okay, so here's the entire pseudocode right here. Here's what it would look like in a flowchart. Okay, notice that the actual calculation is done in a rectangle box. Here's another one you can look at on your own. It's calculating a percentage. I would highly suggest you read that and basically kind of get acquainted with how to do pseudocode that way. Order of operations. Very important that we know how math executes. Okay, I've got 17 plus x plus 21 plus y. Okay, I have 12 plus 6 divided by 3. How do we do that? Do I take 12 plus 6 and divide that by 3? No. Order of operations says we do anything inside of parentheses first. Then, once we basically are inside of a parenthesis, we always take care of any exponents first. Then we do any multiplication or division first, whatever comes. We do multiplication or division, whichever comes first. So I got to start from the left-hand side, I start working to the right. Once I take care of all the multiplication and division, then I basically come back and do any addition or subtraction, whichever comes first. So in this case, I start from the left, I go to the right, up here's division. So I take 6 divided by 3 is 2. Then I go back to the left and I start over. 12 plus 2 is 14. Okay? So 5 plus 2 divided by times 4, I take 2 times 4 first, which is 8. Then I can start back over here. 5 plus 8 is 13. 10 divided by 2 minus 3. So I do the division first. 10 divided by 2 is 5 minus 3 is 2. 8 plus 12 times 2 minus 4. Well, I do the multiplication first. So 12 times 2 is 24. 8 plus 24 is 32. Minus 4 is 28. Yep, 28. 6 minus 3 times 2 plus 7 minus 1. Well, I do the multiplication first, so 3 times 6, or 3 times 2 is 6, so 6 minus 6 is 0, plus 7 is 7, minus 1 is 6. And again, we add parentheses. We do the parentheses first, and again, we have to follow the order of operation within the parentheses there as well. So right here, if I've got 6 minus 3 times 2 plus 7 divided by 3, I do 6 minus 3 first, which is 3, and 2 plus 7, which is 9. So 3 times 9 is 27, divided by 3 is 9. Okay. So again, I would go through the spotlight, go through that, on a pencil paper, kind of walk through how they do it, get a feel for how to do pseudocode. Advanced arithmetic operations, exponent and modulus. Again, I would say set area equals length times 2. Set leftovers equals 17 mod 3. So I would take 17 divided by 3. Whatever the remainder is will be put into leftover. Not the actual number, but the actual remainder gets put into leftover. So if we were to see 6b, we would know that that's 6 times b. 3 and 2, 12, that means 3 times 12. 4xy means 4 times x times y. Again, well, look at that. So this is y equals 3. So L, x divided by, so x divided by 2 times 3. That's basically what that means. So if we look at this guy here, I've got 1 plus r, whatever that comes out to be, is going to be raised to that exponent, and whatever that number is going to be divided by f. Again, another good place to go through on your own and go through these spotlights to kind of get a feel for the pseudocode and how it works. Okay, so variable declaration and data types. So how do we create variables? And we have to say, okay, now that we've created a variable, I have to say what kind of data is going to go in there. So I like to call variables Tupperware bowls. Okay, they're Tupperware bowls. They hold data. But what we have to do is we have to tell that Tupperware bowl what data can go in here. Okay, so we've talked about string data. That's just textual. So if I have a string Tupperware bowl, only thing going there are strings. Okay, it can accept numbers, but once it's in a string format, we can't do any mathematical equations on it. It's just a number. It's for display purposes only. Think of it that way. Any numeric data is in there is for display purposes only. But I have to do, if I have other types of numeric data, I have to tell it, that Tupperware bowl, that it can only accept that type of data. Well, I have integers. I have, well, let's see what they're going to talk about here. So declare integer length. So what an integer is a whole number, no decimal places. So I've just said that I'm declaring a variable called length. And the only thing that can go in here are integer data types. That's it. I can't put in a string. I can't put anything else but an integer data type. That's a number with no decimal places. We have what is called real. Real means decimal places. It's a numeric value that can accept decimal places. And then we have strings. So integers, real, and strings. I will say declare whatever the data type is, and then the variable name. So here I have display what is your age, input age, declare integer age. Okay? Now, there's a problem with that. Here's where I've declared or created that variable age, and here I'm using age. So I'm putting the cart before the horse. I have to have this declare statement before the input statement. So I declare the integer age, then I say display what is your age, then I input the age. Now, can I type in 12.2? No. It says I will only accept integer data. Then I say display here is your value that you entered and display age. I can declare a variable and then put data into it at the same time. It's called initialization. So in this case, I declare a real, that means a number with decimal places, called price, and I'm going to set it to, or initialize it to, 49.95. I can do the same thing here. I can declare multiple variables at the same time. So here I'm declaring an integer of length, width, and height. So I declare length, I'm going to set it to 2, comma, width, they're all integers, set it to 4, and height equal to 8. I can only do that when I have variables that are the same data type. I can't mix and match. I can't say declare integer length, real price. No, I'd have to say declare integer length, declare real price. An uninitialized variable, that means a variable which has not been set to anything, so declare real dollars. So now I have a Tupperware bowl. It's empty, but the only thing that can go in there is real data, meaning numeric data that has decimal places. So that is called an uninitialized variable. So declare real test1, test2, and test3, so those are actually four uninitialized variables. Then I say set test1 equals 88, set test2 equals 92.5, set average equals test1 plus test2 plus test3 divided by 3. And then display the average, your average test score is, and then average. Numeric literals and data type compatibility says many programs you have seen so far have numbers with written into their pseudocode. For example, the following statement which appears says set dollar to 2.75, and the following statement which appears set price equals 100. The number that is written to the program pseudocode is called a numeric literal. We've seen string literals, but numeric literals are just that. They are actual numbers. So 2.75 is a numeric literal. I'm making dollars, a variable, equal to a numeric literal. Declare integer I. Set I equals 3.7. That's an error. Why? An integer is a whole number. There are no decimal places. Declare integer I. Set I equals 3.0. That is also an error. Even though it's a 0, since I said 0.0 on the end, it's expecting that to be a real number data type. Be careful when you divide by one integer to another. More than likely it's going to create a real numeric data type. So make sure that if you are saying some variables equal to this integer divided by that integer, that's probably going to need to be a real data type. Okay, so we've talked about variables, we've talked about initializing variables. We also have variables that are called constants. Well, let's not call them variables. They're just called constants. And what they are a container of data, but that data can never change. Okay? So if I say set amount equal balance times 0.069, I could do this. I could say constant real interest rate. Now notice that whenever I make something a constant, I make the variable name all uppercase. That lets the programmer know whenever I see a variable that has all uppercase, I know it's a constant. So it's a way to differentiate variables so that the user knows what they are, or the programmer knows what they are. So once I've executed this line, and we can do this in most any language, I create a real constant, a numeric constant number called interest rate, and it's set to 0.069. Once that constant is set, it cannot be changed. So if later on I said interest rate equals 0.082, it would basically error out saying, sorry, that's a constant. You cannot change it once it's set. So then I can say set amount equals balance times interest rate, and now I basically have done a calculation. So constants cannot be changed. Once they're set, they're set. So one of the things we have to do is what they call hand tracing a program, or what I like to call desk check. Okay? What desk checking is you become the computer. You pull out a piece of paper and then you step through the code and execute the code itself. Okay? So in this case here it says declare a real variable called test1, declare another real variable called test2, another one called test3, another one called average. So now I have 4 variables, test1, test2, test3, and average. I'll then go ahead and say set test1 equals 88.0, set test2 92.5, set the average of test1 plus test2 plus test3 divided by 3, and give your average score. So I would type in this first box 88.0, 92.5, nothing for test 3, and then the average, I would take those two numbers, add them together, divide by 3, and that would give me the average. So I'm actually becoming the computer. I'm actually going through and executing the code on paper, making sure that my logic works. Documenting a program, we just put 2 slashes, and anything behind that is a comment. We're going to say the code actually ignores anything that has 2 slashes in front of it. And that I think works in most languages, but every language has a way to make a comment. So in our pseudocode, we're going to use 2 slashes. So again, when we write our actual program from our pseudocode, we are going to keep those comments. We're going to put / or whatever language, that language tag makes a comment. So here I have calculate the interest, set interest equals balance times interest rate, add the interest rate to the balance, set balance equals balance plus interest rate, or interest. Okay, so we got comments in there explaining what we're doing. Again, I would go through the spotlight, go through it, get to know what we need to do there. So design on our first program. So we got this program. It's going to be called batting average. And baseball batting average is commonly used to measure a baseball player's batting ability. You use the following formula to calculate a player's batting average. We take the hits divided by the times at bat, and that will give us our average. Okay. So we're going to get input. We're going to process the input. We're going to give output. So the input that is received, to determine the program's input requirements, you must determine the pieces of data that are required for the program to complete its task. Okay. So we are going to get the number of hits, and we're also going to get the number of times at bat. Okay. So number of hits. Can that be an integer? Do we need a decimal place? No, it can be an integer. Number of times at bat, same thing. That we don't need a decimal for that. So those can be integer data types. What about the average, the batting average? That probably needs to be a real, because when we divide by one number and another number, we're probably going to get decimal places. Some process. So the process here is we're going to get that data from our users. We're going to then calculate the average pay by taking the hits divided by the times at bat, gives us our average. So I declare an integer hits, I declare an integer at bat, I declare a real batting average. Then I say display into the player's average number or number of hits. Then I go ahead and say input hits, I get the hits. I display the number of players, number of times they were at bat. I basically then get that as input. Again, those are integers. And then I say set batting average, which is a real, and that's equal to hits times at bat, or divided by at bat, and I basically have a number. Then I display the player's batting average is batting average. Okay, put those all together. This is basically what it would look like in pseudocode. I can give that pseudocode to my programmer. The programmer can then write that program in basically that particular language that the programmer is writing in. Here's what the flowchart would look like. Okay, so again, go through the spotlights, go through those, sit down and work through them. It's going to get you very, 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 very used to pseudocoding. If you want to use flowcharting, there is a program called Visio. And we can get that from Midstate. Will basically load that on your computer, your personal computer. And there what you can do is click on this basic flowchart. We don't want to use any of the other symbols. And we go ahead and click Create. And what we can do is I can say Start. I will actually type the word Start. Oh, come on. And then I will grab, here's data. It's my parallelogram. I might have a couple, 2 or 3 of those. Here's a process. Okay. And then I might have another display. And then I have a stop statement. Okay. Then I have to basically put these guys all together. Where I can actually grab this guy let's see here. So, well, anyways, you kind of get the gist there. You put the arrows in there, and you can fill each one of those boxes in with different things, and basically go from there. So, and that's how you can do flowcharting. We'll discuss it more in class, or if you need any help, we can basically Skype as well. So, anyways, that's it for chapter 1 and 2. These we posted out there, and you can look at these all you want. If you have any questions, make sure you give me a call.